Hello, this video is on fun with sequences. There is an encyclopedia of integer sequences and we start with abundant numbers. In R-Instat, get a data frame with 500 rows. Then, use the abundant key on the integer keyboard of the calculator. Call the column abundant. To understand the abundant numbers, we now get their divisors. So, 12 is the smallest abundant number. We see the divisors and they add to 6 plus 4 plus 6, which is 16. And 16 is more than 12, so 12 is an abundant number. The difference 4 between 12 and 16 is called its abundance. Looking down this list, we see 2 is a divisor of all the abundant numbers we can see. So, perhaps all abundant numbers are even numbers? Wikipedia has articles on each of the sequences. The article includes a pictorial representation of the number 12 and some interesting properties. One property is that all multiples of an abundant number are also abundant. So, as 12 is abundant, so are 24, 36, 48, and so on. It follows from that property that there are an infinite number of abundant numbers. There are also some odd abundant numbers, but there don't seem to be so many. The smallest is the 232nd abundant number and is 945. So, as every multiple of 945 is abundant, it follows that there are an infinite number of odd abundant numbers. There seems just one more in our list. It is the 386 and is 1575. So, almost all abundant numbers have 2 as a divisor. Many have both 2 and 3 because they are multiples of 6. The 2 odd numbers have 3 as a divisor, but not 2. From Wikipedia, we learn that 5,391,411,025 is the smallest abundant number without either 2 or 3 as a divisor. We were quite surprised that we could get its divisors, though we put them into the output window because we couldn't see what we could do with them. The abundant number 12 is also called semi-perfect because a subset of the divisors add exactly to 12. 18 is also a semi-perfect. For example, 3 plus 6 plus 9 is equals to 18. If an abundant number is not semi-perfect, then it's called weird. We don't have a way of easily calculating weird numbers, but according to Wikipedia, the smallest weird number is 70. It is in the encyclopedia where we see that 836 is the only other weird number in our list of the first 500 abundant numbers. It would be nice to be able to add the numbers in the div variable and so to calculate the abundances. That's not quite so easy. The first step is to get rid of the C and the brackets. That uses the transform dialog. We start with the third character to omit the C and the open bracket at the start, and go to -2 to omit the ending closing bracket. Now split the dialog. Wow! That has produced 39 columns. That's because 1680 seems to have so many divisors. It has produced blanks instead of missing values too. We replace them with the Prepare Data Frame Replace Values dialog. The final step is to use the right-click menu and change all these character columns into numeric ones. Now at last, use prepare, column numeric, row summaries as shown. Now it's more interesting. Back to the calculator. Oh, that's an R-Instat surprise. I'd forgotten that the abundance numbers are a special type of integer. So, the division gives the result in a fractional form. I quite like that, except this time we need the actual numbers. Right-click and duplicate the variable into abundance1 and make the result numeric at the same time. Then, repeat the calculation to give the relative abundances in a form that can be used. We are now on row 6, where 36 is called a superabundant number. Its relative abundance is larger than any smaller value. Looking down the list, 48 is superabundant and so is 60. The next is a bit further and it is 120. And this is the first with an abundance as high as 2. Perhaps it isn't a surprise that the next is 180 and then 240 and then 360. This is indeed another sequence we can check from the encyclopedia. A graph will be fun. Use describe, specific table stroke graphs, line plot. We can choose the option to add the peaks to the plot. We see that many have abundances only slightly greater than 1. The last superabundant number in the graph is 1680, which has an abundance of more than 2.5. We liked abundant numbers so much that we have added a short supplementary video on the superabundant numbers, and we have others on triangular numbers and Fibonacci numbers, and of course on factorials.